On slide 68, we turn to model variations on the random intercept latent transition analysis theme. And there are many such model variations and model extensions that are possible in the framework that Mplus provides. For instance, standard LTA typically assumes and works with only lag1 models for the latent class variables. So if you have 3 time points, the latent class variable at time 2, C2, is regressed on C1, C3 is regressed on C2, but C3 is not regressed on C1. It is quite possible to add lag2 and even lag3, etc. for these variables. And in fact, for these data, there was significant evidence for a lag2. We can do a likelihood ratio chi-square difference test and find that to be significant. So that could be explored to see how much adding to the model, making it more general, changes the interpretations, changes the results and the transition probabilities. There was also some evidence for correlated residuals for the categorical indicators across time. Such residuals are possible to add for these models, and one can also explore how much adding such residuals when they are significant changes the interpretation. You can also add distal outcomes, that is some variable that is somehow predicted by what goes before it in the LTA model, either probably mostly then in terms of the latent classes and probably mostly in terms of the latent class status at the end of the process. You can also add time trends for this kind of a model. That is, we've talked about the random intercept, but we can also add a random slope, or at least a fixed slope, to allow for a time trend. I investigated that and only found evidence for the need of this for the reading data, where there is a natural upward trajectory in terms of reading achievement. And in this general framework, we can also work with multiple processes, that is more than one LTA going forward, and we can actually have processes that have cross-lagged influence, so a cross-lagged RI-LTA in line with the RI cross-lag panel model, RI-CLPM model. And of course you can add to this multi-level RI-LTA. That is, you have time within individuals and then individuals within clusters such as schools or communities. That's a feature that we have not added here yet into Mplus. One key question though is if these LTA extensions are sufficient to capture the essential parts of the data. Is LTA the right type of model? Are we fishing in the right pond, so to speak? And you may particularly focus on whether or not classes or dimensions should be included, should be the dominating description of the data. So we can, from this perspective, we can contrast latent transition analysis and the longitudinal factor analysis that we talked about in previous segments. Now, longitudinal factor analysis has many continuous latent variables, many factors, which typically leads then to high dimensional integration for maximum likelihood, because we have categorical outcomes. That can be heavy for ML, but it could be very easy for Bayesian analysis. Now for LFA, longitudinal factor analysis, the number of dimensions turn out to be the number of time points times the number of within factors plus the number of indicators. So if you look at the model at the bottom here, we have 2 time points, t equals 2. We have 1 within factor, so t times 1. So that 2 times 1 plus the number of indicators, 3. 2 plus 3 is 5 dimensions of integration for ML. It's doable, but a little bit heavy. For the mu data, we have 4 time points, 1 within factor, 2 indicators, so that turns out to be a 6-dimensional integration. For the dating data, we have 3 time points, 3 indicators, so it's 6 dimensions again. And for the reading data, we have 4 time points and 5 indicators per time point, so it turns out to be 9 dimensions of integration. Now, I actually tried this and contrasted the findings, the model fit values from LTA with LFA using maximum likelihood. I could have done this using Bayesian analysis also, but I wanted to relate the results back to the ML log likelihood and BIC values we got for the mixture modeling of RI-LTA. You could do Bayesian RI-LTA as well and then compare and do Bayesian analysis for all models, and then you can compare the so-called PPP values. But here we go with ML. So for the mu data, RI-LTA has 9 parameters, and this log likelihood and this BIC value. For the factor analysis, so no mixtures, we have 16 parameters, 7 more parameters. The log likelihood is a little bit better. However, we cannot compare, we cannot do a chi-square difference likelihood ratio test here, because we have a mixture model in one case and we have a non-mixture model in the other case, and we have different number of random effects in the model. So the naive chi-square difference test would probably be wrong. This is a little bit better likelihood, but is it worth it by adding 7 more parameters is the question. And I think BIC is the best measure to answer that. And it turns out that BIC gets worse for LFA. So here, for the mu data, we could be satisfied with staying with RI-LTA. For the dating data, the LFA has considerably fewer parameters, but it also has a worse log likelihood value. And you see that you're then punished for the worse log likelihood value despite having fewer parameters, in that BIC is considerably worse than the RI-LTA BIC. So I bold the best BIC values here. So for both the mu data and the dating data, we go with the RI-LTA model and not the LFA model. Now for the reading data, RI-LTA has 40 parameters, LFA has 29 parameters, so considerably fewer parameters. But lo and behold, the log likelihood is better for LFA than RI-LTA, even though we have fewer parameters. So clearly then BIC is going to win. You have a much smaller, much better BIC for longitudinal factor analysis. So you should not go with this RI-LTA model that I talked about. In this case, you should go with longitudinal factor analysis. Turns out that I should mention though that this is 9-dimensional integration, so the log likelihood value is a little bit difficult to pinpoint exactly. But it's probably close enough so that the better BIC value is a trustworthy indication of a better model. Now for the LFA, you can look at then the indicator variances, the random intercept variances, which reflect the measurement non-invariance across individuals for the 5 different binary indicators. So letter recognition has a large variance component relative to beginning sounds and ending letter sounds and sight words, whereas words in context is also having a large variance component. So a large degree of measurement non-invariance for the first and the last indicator. So then you can speculate about that substantively, why does that happen? Does it have anything to do with the fact that letter recognition is the first reading domain that you master, and words in context is the last domain? You can investigate that and think about that. And in this model, actually, in this longitudinal factor analysis model, I bring in the means or thresholds. That is, I have threshold invariance across time and allow factor means to change and factor variances to change across time. And you find then that the factor means increase significantly, except between spring, kindergarten, and fall of first grade. Maybe then reflecting that well-known summer drop problem. So more generally then, this raises an important question. Can we use a model that fits much worse than another model? So that is, can we use, for instance, this reading data RI-LTA when we know that there's a much better model, longitudinal factor analysis? Well, that's an interesting question. The immediate answer would be no, you shouldn't use RI-LTA when you know about this model fitting so much better. But is there any part of the RI-LTA conclusions that are useful? Can the model be used for some purposes? For which purposes can it be used? And you can also ask, what if you fit an LFA model which fits the data much better, and then try to extract the type of information that you were interested in when you formulated the RI-LTA? That is, work with a continuous latent variable model, but try to deduce implications in terms of latent classes. Is that possible? That's a question you can ask yourself. Now, you would also say then that none of these models probably fit the data that well. In fact, you could take a look at the reading data. There are 5 binary indicators at 4 time points. That's a lot of cells in the frequency, in the multi-way frequency table. And you can look, for instance, at bivariate model fit statistics, such as those given by Mplus in Tech 10. And you will find that there are many significant deviations from good fit in those bivariate cells. Of course, it's very hard to look at the overall chi-square test based on a frequency table because so many of the cells are going to be empty. So there's always the risk that even this better LFA model is not good enough. That is, it is misfitting. That is, you can find better models than this for the data. So here's a challenge to you, the listener. How would you improve on this modeling? What modifications will you make to make it fit better? And if you find such a better model, is it going to be changing the conclusions that you made based on the LFA model?